Okay, welcome everybody to session 1, where we're going to cover worksheets 1, 2 and 3. So starting with worksheet 1, what we're going to learn about here is the voltage delivery from a cell or a battery. So we're all familiar with these with day-to-day use. We use them to power a range of electronic devices, and these can be disposable or rechargeable depending on the use that we have for them. And a battery is actually quite a simple thing. Basically, it was discovered by a guy called Alessandro Volta, who realized that if you actually put two dissimilar metals, so different types of metal, in connect them with a moist environment, and you connect a wire across those metals, then you can actually detect a current is created. And the reason this works is basically the dissimilar metals create electrons which flow around the circuit from the anode to the cathode, so the two terminals that lie within the moist material. And in order to stop all that charge building up, all those electrons building up on the destination, the cathode, then what happens is there is what's called an ion exchange. So basically, as an electron is created with a chemical reaction at the anode, that electron is lost from an atom, which creates a positive ion, and that positive ion flows through the material to the cathode, where it can meet up with the electron that's gone around the circuit, and they can create a full atom again inside that material. That material, that moist area, is called the electrolyte, and it's that is the key part that allows a battery to run for a certain length of time. Now, what actually happens in a disposable battery, that chemical reaction is kind of used up during the lifetime of the battery. So that's why batteries eventually go flat, their voltage is reduced, and you have to replace them. Whereas rechargeable batteries have a kind of reversible chemical reaction at both the anode and the cathode. So when you send the electrons the other way around the circuit by charging it, then what that does is that changes the chemistry that's taken place and gets you back to your original state. So they're called a primary and a secondary battery. A primary is the disposable battery, and a secondary battery is the rechargeable battery. And so there's a number of different types of battery we use every day. These are simple alkaline batteries. They're cheap. You can buy them from shops. They're a standard, so you can power a number of devices with these. But they're not perfect. They don't deliver a huge amount of current. So you've got a current that requires much more energy, then you might move to a different type of battery. So the difference in battery technologies usually depends on the metals that form the two electrodes, the anode and the cathode, but also the types of the electrolyte, and also some kind of design aspects such as the shape of the anode and cathode, how the materials are spread out along the battery. And with all these changes, we can tweak certain properties of the battery. So for instance, if we wanted to start a car, that requires a large amount of current but for a short amount of time, which an alkaline battery doesn't produce. So for that case, we'd probably use a lead-acid battery, which is in the majority of cars that we buy today. So lead-acid batteries are very good at providing a large amount of current on demand, but they're heavy. They're not particularly high in energy density, which means you don't get a huge amount of total charge in the battery for the weight of the battery. So for instance, the lead-acid battery in your car is probably only 4 times the capacity of some mobile phone batteries that we see these days. So basically, they're not ideal for things where you want a fairly low mass. Other types of battery that are increasingly common include things like lithium polymer batteries. So the batteries that we're using in our mobile phones, the batteries that are used in electric cars, use lithium polymer batteries, which are excellent because they have a very high energy density value, which means we get a lot of charge in the battery for a fairly small amount of weight, which is why they're good for portable devices. They can also give a large amount of current as well, similar to lead-acid batteries. But the problem with that is if there is a problem with the battery, or you accidentally short-circuit the battery, a huge amount of energy can be released in a short amount of time. So some of you may remember Samsung had a problem recently with, I think, their Note 7 device, where short circuits on the battery actually caused the battery to fail in a really bad manner. Basically, the huge amount of current that was caused by the short circuit caused the battery to overheat. It could actually catch fire and give off gases, which was why there was problems with having them on aircraft and things going forward from that. So basically, we have to choose the right battery for the given task based on the weight of the battery, the current supplied by the battery, and also the voltage that the battery can supply as well. These standard AA batteries develop about 1.5 volts. When they're fully charged, it's a bit more than that, and as you use them, it drops down a little bit, and that's due to the chemistry of the anode and cathode and the electrolyte within the battery. It's purely determined by the physical behaviour of the battery itself. Now, other batteries or other cells which form batteries have different voltages. So things like nickel-cadmium batteries have voltages of 1.2 volts. Also, nickel metal hydride batteries have 1.2 volts. And that's important because basically if you have a rechargeable AA battery, the chances are it's a nickel metal hydride battery. If it was 15 years ago, it would have been a nickel-cadmium battery. But these can only provide 1.2 volts compared to the 1.5 volts of a standard kind of Duracell that you'd use in your portable devices. So for some applications, that slight drop in voltage can actually cause the device to not work as well as it could. It might be slightly more temperamental using rechargeable batteries. So this is particularly a problem for things like camera flashes, where you require quite a high voltage in order to generate a flash on a camera if you've got an external camera flash. So another popular battery we mentioned before are lead-acid batteries. So each lead-acid cell, once again, because of the nature of the materials, the physics of the materials, will generate 2 volts. So actually, if we're looking to have a battery in our car, which requires 12 volts for the starter motor, what we do is we take these lead-acid cells and we connect them what's called in series. So we connect them in line with each other. And what actually happens is we can add all those voltages together. So if we have 6 of those all connected together, we have the 12 volts that's required for powering the car, basically. And this is what we do all the time with cells. If you have electronic devices like toys or any kind of device that takes an AA cell, you'll notice that you often put in 3 of these, which gives you 4.5 volts, or 6 of these, or 4 of these, which gives you 6 volts, in order to power the device. So what you're effectively doing is connecting the end of the batteries all together in a line, and so the total voltage across them is basically the sum of each battery voltage. And that's used inside batteries as well. So if you ever took apart a PP9, which is the square battery that once again you use quite often in remote controls or toys, that actually consists of 6 cylindrical batteries that look like this, but they're a quadruple A size, so they're much smaller. So the 6 of those all connected together inside a PP9. Okay, so let's get to the experiment, and we will work through the worksheet. I'll show you here using the Locktronics hardware how we can go through the activities here and how we record the measurements that we take. Okay, so first of all, an introduction to the Locktronics equipment. So this is basically the main sort of Locktronics board, and it consists of, as you'll see, is a number of kind of posts that stick out of the board, and each of these posts allows us to attach the individual components here that you can see here, which can be just simple wires. So these connect with the springs that just slot into the thing between the posts. And so these simple wires just make a connection between neighbouring posts. But we have a whole load of different components that we can slot into here that we'll use as we work through each of the worksheets. So what we're doing here in worksheet 1 is we're going to measure the voltage across each one of these batteries here. So in order to do that, we actually slide the battery in to this, so if we get this the right way around, so slide the battery in to this Locktronics accessory here. So this allows us to connect the battery to this post design that we have that we have on the boards. So we have to make sure that we connect the battery the right way round. So we have a positive sign on the battery here, and that goes next to the long sign for the battery symbol. So in any kind of circuit drawing, we describe a battery with a long line and a shorter line. So the long line is a positive terminal and the shorter line is a negative terminal. So that's important to enable us to tell how the battery works. So what we're going to do here is we're going to place a battery into our board, and we're going to measure the voltage across it. So I'm just going to bring out the two tails for this battery here. So we're going to measure the voltage at these two locations here. So how do we do that? Well, what we do is we use what's called a voltmeter. Okay, so what we have here is a voltmeter. So this allows us to measure lots of different properties of an electric circuit. So if we look at the settings of the voltmeter, we can rotate this dial here, and this allows us to choose how that voltmeter is going to function. So on the top, we can measure what's called resistances of circuits and components, which we'll come on to look at in later worksheets. We also have voltage measurements down this side of the voltmeter. And these are split into two types. One is what's called DC measurements, or direct current measurements, which is where the voltage isn't changing in the circuit, and this is what we'll use today. But later on we'll look at what's called AC circuits, so circuits where the voltage actually varies with time, and that's why we need to use this part of the voltmeter here. On the other side we can measure currents, and we'll come on to this in worksheet 2. So down the side here we can measure different current values, and once again we have DC current values here and AC current values here. And for each value, we've basically got a range, which basically just sets the range of voltages or currents over which the meter is going to be sensitive. So we can set, if I change this here, so I can set it on a 2 volt range for looking at the voltage across this battery, if I assume that it's going to be roughly 1.5 volts. So we know that that's going to fall within the range. Right, okay, so a few things to note with the multimeter. We have to make sure that we connect the leads in the right ports on the bottom of this. So here I'm going to connect the black lead into the black COM port, and then I can connect the red lead into 3 different ports. But these here are for voltage measurement, for current measurements, and the one here, because I'm measuring voltage, is on the right hand side, so I need to make sure that that is slotted into that part of the voltmeter. So then I want to ideally measure, use the red lead to measure the positive voltage of the circuit. So in this case, I know that the positive side of the battery is at this end here, because I've got the long symbol of the battery symbol here. So I'm going to connect my red lead into that position there. And then the reference lead, or the black lead, I'm going to connect at the negative side of that. So I'm going to connect that into that point there. So this is all good. The good thing about using a multimeter for voltage measurement is it's very difficult to damage the multimeter, because it has such a high internal resistance that it can't be easily damaged by the high currents you could get from a short circuit or that kind of thing. So I'm fairly safe, so I'm going to turn that on there and see what I get. And so you can see the reading here. That's actually measuring 1.599 volts. So what I'm measuring here is a very healthy battery. It's fully charged at 1.59. If I left this for a long time, and particularly if I put a bulb or something in the circuit, I would start to see that reduce as the energy in the battery is being consumed. In fact, you can see it kind of ticking down a little bit as we speak. So basically, that's what I would expect to see for a healthy cell. This is a fully charged battery, which is showing us about 1.6 volts, so 1 volt over the nominal value of the battery. So this is basically the experiment I'm doing, which is part A in worksheet 1, so just a single battery. So next experiment, I want to see what happens if I'm measuring the voltage across 2 batteries, what's called in series. So now I'm going to put my next battery into the circuit, so I'm going to have to put one up here. Do it this way around for now. I can connect these 2 leads together, and I'm now going to see what the value is across 2 different batteries. So if I put the lead in here, you'll now see that the display on the multimeter is reading 1. And what that's telling me is basically, because the reading isn't changing, it's not reading 1 volt, it's telling me that I'm now out of range. Because my range setting was only going to be set to 2 volts. Now, if the first one was 1.6, every chance this is going to be about 3 volts. And so what I need to do is just increase that range setting. So I'm going to increase that range to 20 volts now. And sure enough, when I do that, I'm now getting a reading. So I'm getting a reading of about 3.2 volts, which is perfect. I saw that I've got 1.6 volts across the first cell, and now here I'm reading 3.2 volts across both cells. So basically, I would record that value for experiment B on worksheet 1. Okay, so what we've learned here is basically if we connect one battery to another, but if I connect the positive terminal of one battery to the negative terminal of the other battery and then measure the voltage across the two, then that's going to be the sum of those voltages. I can double check that. If I go back and just measure the voltage across the new battery by putting my terminals here, then sure enough, I'm getting a reading of 1.6 volts again. Okay, so it all seems to make sense. We've not broken physics. So we've probably got a good idea of what's going to happen when we connect 3 batteries in series. So I'm just going to do that now. I'm going to need to go a long ways on the board to fit everything in, but if I put my first battery there, just one linking thing, I don't actually need 2 in this case. Connect my second battery. So here I've connected the positive terminal of one to the negative terminal of the other one. And I'll put my final battery in the series in at the end here. And I'm going to measure from the negative end of the line of batteries here to the positive end of the line of batteries there. Just move the cable out of the way. And as expected, we're getting a reading of 4.8 volts across the lot. So it's as we'd expect. Basically, if each battery is 1.6 volts, then when we connect them all in series, we're going to get a total voltage across the batteries of 4.8 volts. So this is all good stuff. It's all making sense. Okay, so next we'll go on to the second part of the worksheet, where we're going to connect each of the batteries in parallel and see what happens then. So basically, I'm just going to change the arrangement of my batteries now, and I'm going to connect my batteries like this. This is really easy because I don't need to connect any link cables. So here, if we look closely, then basically I'm connecting the negative terminals of the batteries together and the positive terminals of the battery together here. And what I'm going to do is measure the voltage across the batteries in parallel. Okay, so what I can do is actually to make this a little bit more obvious. Okay, so I'm going to connect these two like this. I will take the connection out of the middle of the batteries and down here. And I'll just measure the voltage between this side and this side. So basically it's these common terminals. These lines indicate what's connected. So I've connected all the negative sides together, all the positive sides together, and now I'm going to connect my multimeter here again. So if I put these in here like this, then what we get here is instead of before where we connected them in series, we get all the voltages added together. Even though there's 2 batteries connected in parallel, in this case, the resulting figure on our multimeter is just the same as one battery on its own. Okay, so what we have here is basically we're learning that the batteries connected in parallel will only produce the same voltage as a single battery. However, each battery is able to produce a certain amount of current. And so what happens is if we connect batteries in parallel, then the amount of current that that battery can produce for a circuit is actually doubled. Okay, so if we had something that requires a lot of current, then basically this would be a way to address that by adding multiple batteries into the circuit. What I can also do is add my third battery into the circuit again, so I'll put that in the circuit up here, click that in place, and once again I can see that that hasn't changed the total voltage across the circuit. So kind of as I'd expect, if we didn't see a difference with 2 batteries, by adding a third battery in the circuit, we're seeing that once again the voltage is unchanged. However, once again, if I had a very high current requirement, this arrangement would now be able to provide 3 times the current of a single battery on its own. So it actually gives us improved performance when we consider it in terms of the current that's available in the circuit. Okay, so basically what you need to do after completing this worksheet is then do the worksheet quiz. So if you go into Canvas and look in the assignment section, then you'll see, or in the learning material section, you will be given a link for the Canvas quiz to answer the questions on worksheet 1. So basically there's questions about the experiment that we see here, and some general questions about how batteries work, and also considerations about when to connect batteries in series or parallel for certain applications. Okay, so that's the end of worksheet 1. We'll now move to worksheet number 2. Right, okay, so for worksheet 2, we're going to look at current in circuits and how that's affected when we have different loads in the circuit, different components that are converting electrical energy into something else. And also we're going to look at what different configurations of the circuit do to the current that's going to flow through it. So basically, for this experiment, I'm no longer going to use batteries because it's a bit of a waste, because what I'm going to do is consume the batteries. I'm going to have to pay to replace those. So what I'm going to do is I'm going to replace that with this component here, which is actually, it takes an input from a power supply. So I've got a transformer that can output 12 volts. I connect that 12 volt transformer in here, and that provides 12 volts across these 2 terminals here. So it basically operates in a very similar way to the battery part, but it's just something I can plug into the wall, so I don't have to keep replacing batteries, which will be a problem if we're doing these experiments over and over again. So here is the end of my power supply. Just double check, so the power supply here is configured by turning this dial. Make sure that's set to 12 volts, so I know that's the case. Plug that in here, and I'm going to connect that to my component here. I do have a multimeter here, remember from the last experiment. So let's just double check that we have 12 volts appearing across this. I'm going to connect once again the red lead to the positive terminal, the black lead to the negative terminal. Oops, on the wrong setting. Connect that there, and sure enough, we have 12 volts across that power supply. So that's good. We know that everything's going to work. Right, so I'll just disconnect that for now. So now what we're going to do is we're going to connect some bulbs to the circuit. So we have a bulb here, a lamp. So I'm setting this up in the series circuit that's shown in part A on worksheet 2. So we've got 3 bulbs that are all arranged sort of like in sequence. So one end connects to the next end of the bulb, and it goes out of the positive end of the battery and returns back into the negative end of the battery. So I'm going to lay that out here using the Locktronics board. So I'll do one there. Let's see, we can do it really straightforward actually. I just do another link pin in here. I can add another bulb there, another link pin there, another bulb there, another link pin in here. So you can see that I've connected all these together, and what I've got is a very dim glow. You can just about see here. Maybe if I turn this top light on, we can see we've actually got a very, very dim glow on each one of these bulbs. So is it easier if I show? Yeah. So it's not particularly bright, but some current is flowing through the circuit. So let's see what that recorded current is. So basically what I want to do for this experiment is I want to measure the current at this point, this point, this point, and this point, and see what those values are in my circuit. So the easiest way to do that is to connect to the multimeter, but measuring current with a multimeter is quite considerably different from measuring voltage, because the multimeter has to go in series in the circuit. So all the current has to flow through the multimeter to get an accurate reading. Voltage measurements, you can just connect to the multimeter between 2 points on the circuit, and it will tell you the voltage between those 2 points. Whereas for current, it has to flow through the multimeter. So what I'm going to do is I'm going to remove this circuit here. I'm just going to unplug the lead, which is good practice. Remove this circuit here. I'm going to connect, once again, I'll connect the red lead to the positive side of the circuit, next to the long part of the symbol there, and the black lead to the negative part of the circuit. So it flows from positive to negative. Basically, if I connected it the other way around, it wouldn't make any difference. It's just the result on my multimeter will be negative, and that tells me that the current's flowing the opposite way to how I'd set it up. So it just gives you a negative value. Right, okay, so I'm going to put that in the circuit here. I now have to change my multimeter from a voltage measurement to a current measurement setting. So I'm going to take that from there and plug it into the red part of the circuit here. And it's really important when you're setting up for a current measurement that you're not causing a short circuit anywhere in the circuit. Because basically, if I connected the current meter directly across the power supply, I would see a large amount of current going through my multimeter, and that would cause the fuse to blow. Now, it's not a big deal. We can replace that fuse, so someone else can use it after we've made that mistake. But it's a slight pain, and basically, obviously, it speeds up the experiment if we're not having to replace fuses in multimeters. So we always have to check our circuit to make sure that we've not got any short circuits. So here, the current's flowing from this point. It's flowing through the multimeter, coming back here, and then flowing through these bulbs and around the circuit. So there's no chance that there's going to be a significantly high current here. So what we can then do is we need to set our current value to something meaningful. So what I'm going to do is set it at something like 2 milliamps, see what result I get and whether I have to change that range in order to increase the accuracy of the result. So let's connect my power supply again. So I'm going to plug this in here, and I'll turn on my current meter. Okay, so I've got the 1 again, so that's looking like it's out of range. So let me just change that to a slightly higher reading. No, still showing out of range. Okay, so when I turn it to the 200 milliamps reading, I'm now getting a value through this circuit of 56.9 milliamps. So let's just... Okay, so that's good because it tells us we've got a current flowing through that circuit. It's quite low, though, which is why we're getting such poor illumination of the lamps in the circuit. So this is kind of what we'd expect. Okay, so that's great. So we know that at point P on our diagram here, we're recording a reading of 57.2 milliamps. So now I'm going to remove those leads again, place back my linked lead there, remove this link lead, and put my next leads in the next location. Connect the power supply, and I'm getting a very similar reading. This is 56.7 milliamps. So it's pretty much the same current that we saw at the previous point in the circuit. So once again, take out the leads, take out the link, and replace this link here at point R. Put my leads in place and connect the power again. And once again, very similar values. So we've got 56.4, 56.5 milliamps recorded at this location. So we're seeing a pattern here. Basically, all these values appear to be the same. So let's just place that link lead back and remove the final link lead. Notice that I've actually changed which way round the red and the black leads go. That's because, once again, the red always has to be the positive side of the circuit. So if this is a positive side, it means it actually reverses when we come back here. So the black lead goes on the left now, and the red lead goes on the right in order to get the right value. So if I connect that back up, yeah, once again, 56.6 milliamps for the circuit here. Just to show you what the effect is, if I do put these the other way around, as I say, it's not going to destroy anything. It just changes the polarity of the measurement. So if I connect the leads the wrong way around here, so I've got the red on the negative side and the black on the positive side, then my value here now becomes negative. So it's not the end of the world, but it just gives you an idea of which way the polarity is in your circuit to go forwards. Right, okay, so disconnect that, and we've completed the first part of the experiment. So we've seen that all these values are pretty similar. So now I'm going to set up what's called a parallel circuit. So here, all the bulbs are in series, so there's one wire that connects all the bulbs going around the circuit like this. And this is actually a very common way of connecting bulbs. If you imagine the bulbs on things like Christmas tree lights or celebration lights, they're normally connected in series, so one bulb after another. The problem is if one bulb blows or fails, then that takes out the whole string of bulbs. So sometimes it can be quite difficult to find out which one has gone. In modern lights, sometimes they're more likely to be connected in parallel to avoid that problem, so you can lose a bulb and not have that issue. But now let's set up our circuit as it's shown in part B. So now we need what's called a parallel circuit. So in this case, what happens is each of these wires has a junction. Oops, no, I need to put that one in there. So basically we have a junction, and so the wire splits 3 ways and goes through the bulbs this way. So let's get some more link products. Okay, so I just need a few more connecting parts, which I can put in here, and one more. And here. So now let's see what happens when we connect our 12-volt power supply again. So I'll add that in here. Okay, and we can see that's much improved. We're getting a much brighter output from the lamps in the system. Okay, so this is working well. So what we now need to do is measure the current at locations P, Q, R, S, T, and U on our circuit board. So we have P, Q, R, S, T, and U. Okay, so let's go through these one by one. So my first measurement is going to be at these locations here. Just make sure I'm set to the right setting, and I put the power on. Okay, so I'm recording slightly higher than this 200 milliamps that I was set on before. So I do increase it to the 2 amp setting, and what I'm seeing now is a reading of 0.325 amps or 325 milliamps. Now there's 1,000 milliamps in an amp, like any other unit. So here the multimeter is set on the amp setting of 2 amps, and we're getting a reading of 325. Or it was. There we go, 325. So basically that's going to be the reading for this first junction in the circuit here. 326 milliamps or 0.326 amps. It's the same value. So I'll take away my junction, replace the link lead that we have there, and move on to point Q. So point Q is actually going through this bulb here. So once again, the red lead goes towards the positive end, and the black lead towards the negative end, and connects the power back on again. And now I'm reading 0.11 amps or 110 milliamps. Once again, it's the same reading. So, okay, so that's about a third of what I was seeing before. So remove that link, put in that link back in, and let's have a look at point R. So this is in our circuit at this point here. So once again, reconnect my circuit, and okay, so I've got 0.109 amps or 109 milliamps again. So once again, this is about a third of the first measurement that we took. So I'm starting to be able to guess what this last one is going to be, but let's record the measurement for S. So I'll take that out. Red goes to positive, black goes to negative, reconnect our power. So the bulb's lighting up, and once again, as we can see on our multimeter here, we're getting a reading of 0.11 amps or 110 milliamps. So basically what we've done is we've split this supply from the power supply into three branches that are all the same. We've got the same number of bulbs in each branch, and what that appears to have done is basically divided that current by a factor of 3. So there's a third of the current flowing through each one of those branches. Okay, so, oops, turn it off. So we just have 2 measurements to go. We have measurement T and measurement U. So T is at this location here. So I'm going to connect these two and connect the power. Okay, so interestingly now we have a value shown on the multimeter of 0.219 amps or 219 milliamps. So we can take a note of that. So that's twice the value in each one of these circuits and 2/3 of the value that we had in our first measurement as well. Okay, so disconnect that. And then finally, I'm going to measure the values at this point U. So I'll put these in here and connect my power again. And we've got a value of 328 milliamps. Or 0.328 amps. Okay, so once again, these are the same values. So that's basically completed the experiments. So we've kind of seen that when we divide the supply in 3 similar parallel branches, then the current is split 3 ways in that. We also saw that when we measured the current at this point here, it was kind of double the value that was going down each one of these branches, which probably tells us that as these 2 branches come back together here, then the current that flows from this point is equal to those 2 added together. Okay, so basically we're seeing these changes when we split the paths in a parallel circuit. We're splitting the current, and when the paths combine back together to go back into the negative terminal, then these are recombined in a similar proportion to the paths. Okay, so now the next part of this worksheet is just to do some calculations yourself. So basically, you need to go and look at the worksheet quiz that's related to this work and complete that. Work through those examples. Use what we've learned here by doing the practical work in order to be able to understand what happens in these circuits. Okay, and now we move to worksheet 3. Right, okay, so now we'll look at worksheet 3, where we're going to do similar configurations to the work we did in the previous worksheet, but now we're going to look at what happens to voltage in series and parallel circuits. So the first circuit I'm going to set up is the series circuit that you can see in part A on the worksheets. So once again, this is using my 12 volt supply, which I can put into the circuit at the location here. And then what I want to do is just create, I'll do this fairly big, a big series circuit that connects all of these bulbs together as before. So let's see if I have enough links. I'm going to do here, here, one down here, last bulb in the circuit here. And I'm going to connect my power. Okay, so we connect my power in there. So once again, as before, these bulbs are glowing, as you can see if I hold it up there, but they're really, really dim. Okay, so basically we do have some current flowing through the circuit. This circuit is basically identical to the one that we had before, so we would expect that the current flowing through the circuit will be exactly the same, which is why the lamps are lighting to the same level. But let's see what happens when we measure the voltage across this circuit. So basically, I'm going to connect the voltmeter, but as I said before, the great thing about voltmeters is you don't have to disturb the circuit. You could just take readings across components or at various locations in the circuit in order to see what's happening to the voltage at various locations. So here, if I want to measure the voltage across this bulb, I can basically just add, I can connect my multimeter to this point here and this point here and turn it on, and that will give me a measure of what voltage we're seeing at that point. Okay, so here we're seeing a voltage measured across that bulb of 4.08 volts. So that's my value here for location P on the worksheet diagram. So next, I want to measure the value across Q. So this is the bulb on the right-hand side of the diagram. So I'm just going to disconnect these, connect them together across point Q. And once again, I'm seeing a very similar value of 4.05 volts across this bulb. So let's do the last one. Now, once again, there's been a bit of a pattern occurring here. So if I measure the voltage across this last bulb, once again, it's just over 4 volts. So in this case, it's 4.02 volts. So basically, all these values are the same. And if I add all these values together, then I'm getting just over 12 volts. So that's what we've learned with this experiment. So let's now move on to, I'll just disconnect that for now, experiment B. So here we're now setting up a parallel circuit. So once again, a parallel circuit is where all the bulbs are on their own individual branches in the circuit. So if I set it up something like this, one there, 2 more to go in. Oops. Okay. Right, so now we have a parallel circuit set up here. So basically, all the bulbs have their own individual branch coming down here. So let's see what happens if we connect the power supply. From what we saw with the current circuits is that we should get a fairly bright light. Good, that's a good start. And so now what I'm going to do is I'm going to measure the voltage across each one of these lamps using the same technique that I did before. Right, okay, so the first one, actually let me just undo it, connect my thing and then power it up again. Okay, so now I'm measuring just over 12 volts for this circuit. So across this lamp, I'm seeing 12 volts, which is equal to the voltage that I'm providing here. So that's an interesting result. Maybe I wasn't expecting that. So try the next lamp in the circuit. Okay, once again, I'm seeing just over 12 volts at this location. So basically, I've got 12 volts across that lamp too. So now the final one, you can guess where this is going. Connect that. And once again, we have 12 volts recorded on the voltmeter there. So basically what we've seen here is that if we connect all the bulbs in series, then that voltage is kind of divided evenly between each one of the bulbs in the circuit. However, here, by connecting this voltage directly across the lamps, then we see a voltage across each one of the lamps that's equal to the power supply that's supplying the circuit. Okay, so we know that the current is reduced, but the voltage is the same across the circuit here. So that's an interesting result. So to complete this work, basically what you need to do is work through the Worksheet 3 quiz that's available on Canvas. Fill in your answers based on what observations have been made during this experiment, and there's a few questions at the end of that based on what you've learned in order to take that forward. Okay, so have a go at that and see how you get on.